0 minus 1 0 1 0, and multiplying first row with minus 1 and add into the fourth row. The fourth row become 1 minus 1 0, then 2 minus 1 1, and minus 1 0 0 1. So 0 1 minus 1 0 0 1. Now the first row, in this matrix first row is as it is, the just changes in the second, third and fourth row. Now next process is, you can see the second row. In second row we have leading entry 1, below that leading entry we want to make 0 in that particular column. So already here is already 0. So we are multiplying second row with minus 1 and add into the fourth row. So 1 1 1 0 0 0, then second row is 0 1 minus 1 1 0 0, third row is 0 0 minus 1 0 1 0, and the fourth row become 1 0 minus 0 0, 1 minus 1 0, then minus 1 plus 1 0, then 0 minus 1, that is minus 1, and 0 minus 0 0, and then 1 minus 0 1. So 0 0 0 minus 1 0 1, right? Now is it a row echelon form matrix? Let's check it. The first row we have leading entry this, below that leading entry we already 0. The second row, this is our leading entry, this 1 is our leading entry, below that leading entry we have 0. In third row, this is our leading entry, right, and below that leading entry we have 0. So I think this is a in row echelon form matrix, right? Now what is our argument? That is, we have non-zero pivots, that means leading entries in third and fourth column, right, among the standard basis vectors. So in third and fourth column we have leading entry, and first and second we have already leading entry. So that's why, so we should add 1 0 0 0 and 0 1 0 0 to S to form basis for R4. So that is the answer, 1 0 0 0 and 0 1 0 0. So our new set S dash, call it S dash, that is equal to 1 1 1 1, 1 2 1 2. These two basis vectors already given in the statement, and these two are linearly independent. We are adding two more vectors of R4. First one is 1 0 0 0 and 0 1 0 0, second one is 0 1 0 0, and our new set S dash is linearly independent, that we already proved. These four vectors are linearly independent, and here we also one important theorem which we already used before, one or two example, that this new set S dash contains 4 elements, and we know that dimension of R4 is equal to 4. S dash is linearly independent, that means this S dash is also a basis for R4, because there is one important theorem that if dimension of V is equal to n and S contains exactly n elements, then S is basis for vector space V if S is linearly independent or S spans V. So using that theorem we can say that this our new set S dash is also a basis for R4. Okay, so here to complete the solution of this question. Next question, question 3b. Prove that the set of all positive real numbers form a vector space under the operations defined by vector addition. We use this vector addition, that x plus y is equal to x into y, right? So and where x and y both are positive numbers, and the scalar multiplication c into x, that is equal to x raised to c for all xy belongs to R plus. And this question was asked in 5 marks. Now just try to understand first of all the question and what is the definition of vector space. For that we have to prove all the 10 conditions, the first 5 conditions for addition and the another 5 conditions for scalar multiplication, right? The first 5 conditions are, first of all, closedness, that means if any 2 element belongs to the set, then addition of that 2 element that is also belongs to the set, that is closedness. Then commutative law, that means for any u v belongs to v, u plus v, that is equal to v plus u. Then associative law, right, u plus in bracket v plus w, that is equal to u in bracket u plus v plus w. Then identity, and then inverse, right. Identity means for any u belongs to v, there exists identity element, call it theta, belongs to v such that u plus theta is equal to u. Then inverse, there exists minus u belongs to v such that u plus minus u, that is equal to 0 element, right. So these 5 conditions are for addition, and the another 5 conditions are for scalar multiplication. In scalar multiplication there is also closeness, then associative law, then 2 conditions are for distributive law, and the last one is 1 into u, that is equal to u. So if these 10 conditions are satisfied for a particular set, then we can say that our set is a vector space, and exactly we are proving one by one all the 10 conditions for particular example. Just try to understand first of all in addition. For that addition we have to use x plus y, where x and y both are positive real numbers, right. So in set, theoretically if we want to write what type of set in the, what type of elements are in the set, that means v is equal to exactly r plus, where x belongs to r and where x greater than 0, right. In addition, for that addition we have to use x plus y is equal to x into y. Okay, so just try to check one by one all the 10 conditions. Closeness, x plus y, that is equal to x into y, belongs to v. Why x into y belongs to v? Since multiplication of 2 positive real numbers is also positive. Okay, multiplication of any 2 positive real number is also positive. Next is commutative law. In commutative, x plus y, that is equal to y plus x, that we have to prove. Now what is x plus y? That is x into y, where x and y both are positive real numbers. Now x into y can be written as y into x clearly, right, and y into x can be written as y plus x using the definition of the addition which is given in the statement in this example. So x plus y is equal to y plus x, that we prove. So commutative law is also satisfied. Next is associative for addition. For x y z belongs to v, we have x plus in bracket y plus z. Now x plus y plus z can be written as y into z, and x plus, this is also positive real number x, y into z, that is also positive real number. So addition of this 2 positive real number can be written as x y z. Now x y z can be written as x y in bracket, outside the bracket z, and then x plus y, and then z. Okay, and that is equal to in bracket x plus y plus z. So clearly associative law, that is also satisfied for addition. Next one is existence of identity element, that is x plus 1, that is equal to x into 1. So that means what? The number 1 is our identity element, x plus 1. Because of x plus 1, we are taking x plus 1, that is equal to x into 1, and that is equal to x. Okay, and similarly you can prove 1 plus x, that is equal to 1 into x, that is equal to x. So 1 is our identity element of the addition in V. Now existence of additive inverse. For any x belongs to V, there exists 1 upon x is also belongs to V, because x is positive real number. Just try to understand, x is positive real number, so 1 upon x is also positive real number. For any positive real number, inverse of that positive real number is also positive. Clear? So existence of additive inverse, for any x belongs to V, there exists 1 upon x belongs to V such that x plus 1 upon x, that is equal to x into 1 upon x, and that is equal to 1. Clear? So inverse of x is 1 upon x and identity element is 1, so that's why here we get 1. Now closeness in the scalar multiplication. Another 5 conditions are for scalar multiplications. So for any alpha belongs to R and x belongs to V, alpha into x, that is equal to x raised to alpha, that is also belongs to V. Now this is quite interesting because just try to understand, x is positive real number, right, and alpha is any real number. So for positive real number, the degree of that positive real number is anything. It can be negative or positive, but the whole number is always positive. Okay, so x is positive and alpha is any real number, so x raised to alpha is always positive number, right, for any alpha belongs to R. So that's why this is belongs to V, because of V is equal to R plus n, that contains only positive real numbers. Now alpha into x plus y, that is equal to alpha into xy, because the definition of the addition which is given in the example, that is x plus y, that can be expressed as x into y. So alpha in bracket x into y. Now use scalar multiplication. The definition of the scalar multiplication, this is equal to xy raised to alpha. So this is equal to x raised to alpha, y raised to alpha, x raised to alpha plus y raised to alpha, and that is equal to alpha into x plus alpha into y. Okay, so alpha plus beta into x, that is equal to x raised to alpha plus beta. Next condition that we want to prove, that in bracket alpha plus beta into x, that is equal to alpha into x plus beta into x. So alpha plus beta into x, that is equal to x raised to alpha plus beta, that is equal to x raised to alpha, x raised to beta, and that is equal to alpha into x, beta into x, that is equal to alpha into x plus beta into x. So the 8 conditions we already satisfied. The 9th one is alpha beta into x, that is equal to x raised to alpha beta, that is equal to in bracket x raised to alpha raised to beta, that is equal to beta x raised to alpha, and that is equal to beta alpha into x. So alpha beta into x, that is equal to beta into alpha x. Now the 10th condition is 1 into x, that is equal to x raised to 1, that is equal to x. So all the 10 conditions we satisfied here. So that's why thus all the exams are satisfied by the given operations of addition and scalar multiplication, and hence V is a vector space, that we prove. Okay, so hence V is a vector space. So this is quite interesting question, and this question was asked in 5 marks. Next question. Question 3c. Find the coordinate vector V equal to 5 minus 1 9 relative to the basis S is equal to V1 V2 V3 of R3, where V1 is equal to 1 to 1, V2 is 290, and V3 is equal to 334. And also find the vector with respect to the basis S in US U with of the basis S with respect to the basis S, that is equal to minus 1 3 2. Now first of all we want to find the coordinate vector V is equal to 5 minus 1 9 relative to the basis S, where S is V1 V2 V3. Okay, now this V, this 5 minus 1 9 is any vector of R3, and this V1 V2 V3 are basis vector for R3. That means what? This V can be expressed as linear combination of V1 V2 and V3, right? That is possible. In fact, any vector of R3 can be expressed as linear combination of V1 V2 V3, but here we want to find the coordinate vector of V, so that's why we are expressing V is equal to C1 V1 plus C2 V2 plus C3 V3, and then we find C1, C2 and C3. That is our main target, to find C1, C2 and C3, and that is exactly our coordinate vector of V relative to the basis S, right? So put the value of V, V1, V2 and V3 in these equations. V is equal to 5 minus 1 9, that is equal to C1 into 1 2 1 plus C2 into 2 9 0 plus C3 into 3 3 4. So 5 minus 1 9, that is equal to C1 plus 2 C2 plus 3 C3. You can see this equation, C1 plus 2 C2 plus 3 C3, then 2 C1 plus 9 C2 plus 3 C3, and then C1 plus 4 C3. Okay, now comparing left hand side part and right hand side part, you will get C1 plus 2 C2 plus 3 C3 is equal to 5, 2 C1 plus 9 C2 is equal to minus 1, and C1 plus 4 C3 is equal to 9. So equating the corresponding component, we get C1 plus 2 C2 plus 3 C3 is equal to 5, 2 C1 plus 9 C2 plus 3 C3 is equal to minus 1, C1 plus 4 C3 is equal to 9. Now to solve these equations, we use augmented matrix, right? Here is the augmented matrix. The first row is coming from the first equations. You can see the coefficient of C1, C2 and C3, that is 1 2 3 and then 5. So the first row is 1 2 3 oblique 5. Then the second row is coming from the second equations. The coefficient of C1, C2, C3, that is 2 9 3, and then minus 1 right hand side. So 2 9 3 minus 1, and the third row is coming from the third equation, that is 1 0 4 9. So here is a 1 0 4 9, the coefficient of C1, C2 and C3 in the third equation, 1 0 4 9. Now we are converting this matrix into a row echelon form matrix. So now you already know that how to convert any matrix into a row echelon form. This is our leading entry for the first row. So that's why we are multiplying first row with minus 2 and add into the second row, and multiplying first row with minus 1 and add into the third row. So the first row is as it is, 1 2 3 5,